Hello, ladies and gentlemen. I am not here today. Got things to do, and I hope this video finds you well. And we are going to transition now into things called series. Everything that you've done in 15.1, 2, and 3 were things that you have dealt with before somewhere in the Advanced Math 8 or in Math 1. So what is nice about 15.4 and 15.5 is that you have not seen what a series is. They're very similar to each other, but the biggest difference is it's a sum, meaning you're going to take the sequence of numbers, but you're not just going to have the sequence of numbers. For example, 3, I'm going to add 2, 5, 7, 9. A sequence of numbers is like this, but a series of numbers is like this. That's what a series is. What we should do right now is to pause the video so that students can write down this information. Go ahead and press the Enter button now. Coming back to you. As I was saying about series are a sum of numbers, and if there is a limited amount of numbers, like 3, 5, 7, 9, I was just adding those 4 numbers, that's called a finite series. Whereas, if we were adding something like this, that went on and on forever and ever, that would be an infinite series. Things that have an infinite series, sometimes there is a sum, sometimes there's not. And you will learn that throughout this section. The difference between finite and infinite. Finite, it ends. There's a countable number. And infinite goes on forever. So what we're going to do is we're going to use another formula, and this formula is kind of neat. It's based off of a student who was posed a question a long time ago. I heard about this story when I was learning mathematics, and it's kind of neat. Somebody once said that they were going to do all the numbers between 1 and 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the math teacher posed that question to the students. The math teacher said, add up all the numbers between 1 and 100. And the students that were learning in this math class, they were supposed to spend all day working on this problem. And there was one very, very bright young man who came up with a faster way to do it. And that's what we're going to base this off of. We're going to base it off of what he decided, a quicker way. He was smart. He learned a pattern. I'll show it to you in just a little bit. If we know how many term numbers there are, if we know what the last term number is and we know what the first term number is, a of 1 and a of n, then what we could do is we can use this formula to find the sum of all the numbers in the series. It's called a series because we're going to add all the numbers in the sequence up together. So that's what we're going to do. I'll show you an example of why this works. You add the first, you add the last together. A of n is going to represent the last number this time. And n over 2 is how many terms do you have? Cut in half. And we multiply it by the sum of the first and the last. It's kind of a neat thing. So now, I want to do example number 3, and then we'll pause for the next part of the notes. I'll show you why this particular formula works in just a second. But one thing I do need to point out to you, underneath n, it says this. Sometimes you will have to solve for this by creating an explicit rule, plugging in the value of the last term and solving for n. And I'm going to put a little star next to this. This is the problem inside the problem. You're going to have to do this. It doesn't come easy. unless you do this step first for some of the harder questions, like number 3. We're going to do that for number 3. Number 3. If you want to start this on a separate sheet of paper and start your first homework question as number 3, I am totally fine with that. It says find the sum of each finite arithmetic series. What does that mean? That means that it ends. It goes from 4 plus 9 plus 14 all the way until we get to 44, but that's where it ends. And what we're going to do is we're going to add up all those numbers, and what we're not supposed to do is we're not supposed to take a calculator and just type in the numbers and add them all up. There's got to be a faster way. The faster way is this formula. This formula is great, except we don't know what n is. N is how many term numbers there are. I know the first. This is a of 1. I know what a of n is. I know what the last is. But I don't know how many term numbers there are. And I could count if there weren't these dots here. But because there's these 3 ellipses, I believe they're called. Because those are there, it means that this pattern continues until you get to plus 44. It doesn't show us those things. We could figure out what goes in the gap, but I'm not going to. Instead, I am going to figure out how many term numbers there are based off of this pattern. So here's what I do. These are arithmetic. I know that if I know what the common difference is, I can come up with the explicit rule for this equation or for this sequence. What's it going up by? It's going up by 5. That's the common difference. Multiplied by n. And as we learned in the last section, we're going to add a sub 0, or the term before the first term. What's the term before the first term? I hope you know what it is. -1. So that means that if I plug in the number 1, 2, or 3, I should get these values. 3, 15 minus 1, it works. 2, plug it in, 10 minus 1, it works. So this equation can be used to find any term value. It could also tell you how many term numbers there are. If I want to know what this is, I want to know what term number that is. If I substitute that in for 44, then guess what? I can find out how many n's there are, how many term numbers there are. All I have to do is solve this equation. This is the problem inside the problem. 45 equals 5n. Divide by 5. Divide by 5. Guess what n is equal to? It's equal to 9. There are 9 term numbers. That is not our final answer. That is what we're going to use this formula. How does it work? Let's use the formula now. The sum of all these numbers is equal to, I have a little n there just saying the sum of all the n, how many terms of all 9 terms, is going to be equal to 9 divided by 2 times by the first term plus the last term. So we do what's in parentheses first, 48, times by 9 halves. 2 goes into there 24 times. 9 times 24. I don't know. Let's do that. 36, 18, 19, 20, 21. 216 is what I'm getting for the sum of this series. Now, just to give you a small short history lesson, why does this formula work? Because that really smart student, just like you, sitting in class goes, God, there's got to be a better way. And what that student realized, that if you add these together, and if I were to actually, let me just kind of continue to write what's here. 14, then if I add 5 to it, it's 19. And then if I add 5 to that, it's 24. If I add 5 to that, it's 29. If I add 5 to that, it's 34. If I add 5 to that, it's 39. If I add 5 to that, then I get to 44. That's what we're adding all together. But here is what that student realized. 44 plus the 4, let's add those together. And guess what you got? You got 48. What happens if you add the 9 and the 39 together, what do you get? What happens when you add the 34 and the 14? What do you get? When you add the 29 and the 19, what do you get? If you take the sum of the outsides and you multiply it by half of how many terms numbers you have, that's going to be equal to the total sum. This student realized it and came up with an equation that we can use for any arithmetic series that we're trying to add up together. It's very, very cool that it works. And this is a lot shorter than taking your calculator and adding and figuring that out and doing all that work, especially if we go more than 9 terms, especially when we start getting into 20 terms and 100 terms and things like that. So the last thing that I'm going to have you write down in your notes is right here. It's this epsilon symbol. So why don't we take a moment to pause this video so that you can write down these part as your notes, and then we'll go ahead and do some problems. Press enter now. Coming back to you. We're going to be dealing with this summation notation. Does that say it anywhere here? It does not. This is summation notation. It's used in this class. I'm not sure if they're going to use it in Math 3 honors, but I know they use it in AP stats and regular stats. So this is an epsilon symbol. It represents a series. It's the sum of all terms plugged into the rule. So this is your first term number. The bottom number is your first term number, meaning we're starting with the number 3. What I mean by starting with number 3 is you plug in the third term. It's not necessarily the third term's value. The last term is 8. That's the last term's value, and we're going to add up from 3 plugged in, 4 plugged in, 5 plugged in. So basically, you take this, you plug it in, and the third term has a value of 28. We're going to add, when you plug in 4, you get 29. When you plug in 5, you get 30. When you plug in 6, you get 31 plus 32 plus, and you go until you plug in the number 8. When you plug in the number 8, you get 33. This is what this represents. There's a rule. This is what term number you're plugging in to the rule to find its value, and then you're adding that value to the next term number, to the next term number, to the next term number, and we're only plugging in whole numbers, integers, if you will. This one starts at 3. You can start at any number. It could be a 1, it could be a 0. Most of the time, if you're lucky, it'll be a 1, but it's not always going to be there. The hard part for a lot of you is this part that's underlined in the notes here. How many terms there are is like, you might look at this and say, well, how many terms are here between the third term and the 8th term? Some of you might think it's 5, but it's not 5. Watch. I have 1 term, 2 terms, 3 terms, 4 terms, 5 terms, 6 terms. So if you see 8 and 3 and you think, oh, there's only 5 terms, you're forgetting to count the 3. 8 take away 3 is 5. That's the difference, but we also are plugging in 3 and we're plugging in the last one. So we have to add 1 to the difference. That's going to make a difference when we go to use this formula. You still have to use n in this formula. How many terms are there? You're going to have to figure that out on a lot of these problems. So, with that being said, we were talking about that. Let's do this problem. This problem is number 8 in your homework. And I think, if my memory serves me correct, I only have 3 more examples for you, so your notes should be done by now. You don't need to add anything else to your notes. All you need to do now is to do some examples so you know how to do the homework on your own. This says, find the sum of each finite series, meaning this has an ending point. We're going to add the number 3. We're going to not add the number 3. We're going to plug in the number 3 and add its value to plugging in 4 and its value and so on. We're going to add all those numbers. But this would be considered the long way. This might not seem very long to you. You might want to do this by hand if it's a small enough range of numbers. So I'm going to let you choose for some of the problems. For some of the problems, this might be easier just to plug in the number and actually calculate what is 28 plus 29 plus 30 plus 31 plus 32 plus 33. You might want to do it that way. If you did, I'm sure some of you would do 28 plus 29 plus 30 plus 31 plus 32 plus 33. Did I type it in correctly? I did. Maybe that's easy. Or what if there were a ton of numbers and you didn't feel like plugging it in so many times? What could you do? What you could do is you can use that same formula that we learned earlier, which was how many terms divided by 2 multiplied by, in parentheses, the first plus the last. So I could plug in the first and figure out that that's 28. I could plug in the 8 to find the last. And how many term numbers there are. What did we say that there were? 8. Take away 3 is 5, but we have to add one more, which is going to make it 6 for our term numbers. Let's see if this is the same value. Either way is correct. My recommendation to you, I would do the top method if there's like 4 numbers or 5 numbers. That's pretty simple. Once you get past that, I might want to start doing this method. It might make it a little bit easier on me. Or maybe you only want to learn one way, and I would recommend learning the bottom way because you can use it for a ton of numbers or just even a small. It works for both things. It's up to you. Okay? But that's what that means. The sum of this number plugged in, that value, and all the way up through the 8th term. Write each arithmetic series in summation notation. We're going to break out a capital epsilon. That means the sum of. I am going to recommend that you call this your first term. There's a pattern here. We need to come up with a rule. That's what goes on the side. And if I know my rule, this is going down by 3. I feel like I need a negative 3n since the common difference is 3. Or going down by 3, negative 3. And what would it be before this, the 0 term, the term before? I feel like it's 13. Now let me just check to see if this is right. Negative 3n, I'm going to plug in the number 3. Negative 9 plus 13 is 4. It works. The only thing I need to know now is, if this is my first term, what's the last term? The last term number. How many is this? If I follow this pattern, how many is it? And some of you may want to fill this in. Okay, let's subtract 3 plus 1. Let's subtract 3 minus 2 minus 3. So there's 2 numbers here. What term number is it? First, second, third, fourth, fifth. This is our sixth number. Now, just in case it's a super huge long, we got lucky here because look at how close that was. What if it was super long? What could I do to figure out what term number that is? It's real easy. You take your rule. And you know its value should be -5, and you're trying to figure out what term number will give you a -5. All you do is just subtract 13. -18 equals -3n. Divide by -3. And then your term number is apparent. That is the value of the sixth term. Sixth term is the last term number. So keep in mind, you can always figure out the term number based off of the rule. The rule can be used for that. That's something that we did not do before. That's why this is going to be a stretch for some of you. Does it ask me to do anything else? Nope. Don't even need to add them up. Just write in the summation notation. Piece of cake. Last example. An embroidery pattern calls for 5 stitches in the first row. First row, 5 stitches. And for 3 more stitches in each successive row. 3 more. Next row, 3 more. Next row, 3 more, ... The 25th row, whoa, way down there, has 77 stitches. Woo! Find the total number of stitches in the pattern. Total number of stitches. That must mean in this row, and this row, and this row, and this row all together. We need to add up all these numbers. Oh, wow, that's a lot of stitches. Snitches get stitches. Why did that come in my head? I don't know. I don't know. I don't know. Okay. Okay. So what should I do to figure out what the answer is? I should try to use the series notation or the series formula to figure out what this is. This is a great time to add up a bunch of numbers, and this is kind of a long ways away. There's 25 numbers. I don't want to do all that by hand. This is a perfect time to use our summation notation formula. Sum is how many numbers I have divided by 2, multiplied by the first number plus the last number. Now let's plug some numbers in. The first number is, the value of the first number is 5. The value of the last number is 77. Notice I'm not using the term number, I'm using the value for these. How many term numbers do I have? Here's the best part. If you start with the number 1 and you go to 25, guess what? It's exactly what you're counting is 25. So now I'm counting, let's go with 82. 25 times 82 divided by 2. Stitches. That's what you get when you play with your brother too much. You punch each other in the eye. No, 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 don't do that. Don't do that. Okay. That brings us to the end of our notes. We'll stop right there. I'll give you some time to do some homework.